Hello, everyone. Good morning and welcome to the webinar, where we will be looking into the results and lessons learned on 5G for CAM from the 5G-MOBIX trial site in Germany. My name is Christoforu, and I am a Communication and Dissemination Officer with ICCS, Communication and Computer Systems in Athens, and I'm also the Dissemination MOBIX. Today, I will be moderating this webinar. Before we get started, I would like to inform you that throughout the webinar, you have the opportunity to submit your questions to the question box that you can find on your control panel. We will take them all, so feel free to do so to submit them, throughout the presentations. In case you're experiencing any technical issues, you can use the chat box that you can find again on your control panel and notify one of the presenters, the organizers, as we'll attend to it as soon as possible. Introducing the speakers and the agenda of the day, I would like the presenters to turn on their cameras. Thank you, and a warm welcome to all of you. Our first speaker for today is Sebastian Peters. Sebastian has received his engineering degree from TU Berlin in 2010 and works in the Future Communication Systems Group for Die Labor, leading the 5G activities across multiple EU and national funded research projects. He has over 10 years of experience in project management of research projects, and he's currently leading the German trial site consortium in the 5G-MOBIX project. He was also responsible for leading the project CCAM deployment task. Today, he will introduce us to the 5G-MOBIX project as a whole and also provide us an overview of the German trial site. Our second speaker for today is Christian Müller-Hirschhorn. Christian has received his PhD degree in physics from the University of Erlangen-Nuremberg in 2016. From 2016 and until 2019, he was a postdoctoral researcher at the Max Planck Institute for the Science of Light. And since 2019 until now, he works as a lead engineer at Valeo. Today, his presentation will focus on market needs and industrial innovation. Our third speaker is Angel Martin. He's a senior researcher at Vicomtech. Dr. Martin received his engineering degree in 2003 from the Carlos III University of Madrid and his PhD in 5G domain from UPV in 2018. His research interests are in the areas of video streaming and quality of experience in 5G networks. And he has been involved in different 5G PPP projects such as Cognet, 5G Meta, and 5G-MOBIX. In 5G-MOBIX, he is involved in the development of media streaming and the 5G experimentation testbed topics. Today, and together with Sebastian, they will give us an insight on 5G for CCAM solutions. Next, we have with us today Dr. Fikret Sevrikaya. Fikret is the research director of GT-ARC, an ICT research institute affiliated with TU Berlin. He has received his PhD degree in computer science from RPI in New York in 2007, and he also has a bachelor's degree in computer engineering from Bosphorus University, which he received in 2000. Besides contributing to the trial site activities, he has been leading also the deployment planning and coordination task in 5G-MOBIX. Today, he will present the results of the German trial site. Last but not least, we have with us today Gorka Velez. Dr. Velez is currently leading the Connected and Cooperative Situation Awareness Research Line at the ITS and Engineering Department of Vicomtech. He also represents Vicomtech in the ETSI ITS working groups and also in the 5G PPP CAM working group. In 5G-MOBIX, he led the use cases definition task, and today he will take us through the trial site's lessons learned. Thank you all for being here, and looking forward to seeing your presentations. I don't want to take any more of your time. So Sebastian, the floor is yours. Give me one.
Yes, good morning and welcome to the 5G-MOBIX project introduction. In the following, I will briefly introduce you to the 5G-MOBIX project. The 5G-MOBIX project is an EU-funded innovation action project that will run until the end of September this year. It has the objective of accelerating the deployment of 5G for connected and automated mobility in cross-border areas. And for this, we have carried out trials along cross-border areas to assess the 5G capabilities for CAM. To qualify the 5G infrastructure and to evaluate the benefits of 5G within CAM context, and also to contribute to issues like standardization and the preparation of the 5G Connecting Europe facility. 5G-MOBIX also focuses on issues beyond technical matters and looks into business and regulatory aspects. The 5G-MOBIX rollout is at a glance. You can see that we have a vast number of countries taking part in the project, with 2 cross-border corridors located in Spain, Portugal, and in Greece, Turkey. And we have 4 complementary European trial sites being located in France, Netherlands, Finland, and Germany. And we also have 2 complementary trial sites in Asia being located in South Korea and in China. In order to conduct real-life CAM testing, many pieces need to be brought together, and this includes 5G networks, vehicles, and roadside infrastructure. So what you see here is the summary of the deployment activities that have been done in the project, including 5G networks of SA and NSA kind. In total, 29 GNBs have been deployed. We have automated vehicles being used for the trials, and enhanced the vehicles with 5G enabled OBUs. And next to roadside units, we have also mobile multi-axis edge computing nodes that are used in the trialing of the use cases. There are in total 5 use case categories with the focus on cross-border operation, and these are advanced driving, vehicle platooning, extended sensors, remote driving, and vehicle QoS support. Today, we will see the German trial site use cases, that is vehicles platooning and extended sensors. Thank you very much.
Thank you, Sebastian. Christian, let's move on with your presentation.
So, is my screen coming up?
Yes, we can see it clearly.
You can see it very well. So let me quickly guide you through market needs and industrial motivation for the use cases in 5G-MOBIX in general in the context of the German trial site. So there is different business potential of 5G for CAM applications. First and foremost, of course, in the automotive industry, where I would like to highlight 2 different sectors. On the one hand, the privately owned car sector. Here we have 2 aspects of business potential. On the one hand side, we would have road safety, where we can think of new applications in terms of augmented reality, getting a closer inspection of the surrounding of the vehicle, and hence a more safe driving experience. And on the other hand, automated functions like emergency steering and emergency braking that can be enhanced by 5G capabilities. On the other hand, apart from road safety, there can also be further comfort functions. Automated driving in general belongs to this category, but also, for instance, teleoperation. So this is for the privately owned car sector, but also in the commercial mobility sector, there is huge potential for 5G and CC-CAM. On the one hand, there can be a reduction of the operational expenditure in public transport and in taxi services, but also in the cargo traffic through a high degree of automation. Cargo traffic then means on the one hand long haul distance traveling, like with trucks and any kind of big vehicle transports on straight highway roads, which is the more or less simple case. But on the other hand, it can also mean urban delivery droids, like this project from Valeo. We do have also, apart from the automotive industry, business potential. For instance, there can be new policy models in the insurance business, just to name one example, where we can have new premium models for cars which are equipped with CCAM functionalities, just based on the fact that they are less prone to finding errors or any kind of accidents on the road. There are, apart from that, also cooperations between different players from the automotive industry and the information and communication technology that can emerge from 5G CCAM applications, which are unforeseen as of today, but this will clearly also play a major role. And finally, I added just 3 dots because I want to highlight that this is not an exhaustive list, but these are just some of the examples that we considered. Here's a plan of different business relationships of stakeholders for V2X applications. This is based on the 5GAA application layer reference architecture, and it's very much focused on the automotive industry. We can see that the main source of the business will be, in the end, the vehicle owners, be it privately owned or commercially owned. And there are different arrows indicating the business relation. On the one hand, there will be business between the vehicle owners and road traffic authorities. So be it the public sector or privately owned roads where road infrastructure is being set up. So either there will be taxes paid or tolls being paid, which refinance the setup of the road infrastructure. On the other hand, of course, people are buying or leasing cars, so the purchase of vehicles from the OEMs is one business path. And then if we prolong this path, there is of course also equipment being bought by the OEMs from the tier 1 suppliers, and also the subsequent different tiers which are supplying the tier 1s and afterwards. There is then, of course, in terms of the services that are provided, businesses between the OEMs and the service providers. So in case there is any functionality which is part of the basic configuration of the vehicle, this would be business between the OEM and the service provider directly. In case there is any extra equipment which the vehicle owner will buy after the market, after the vehicle has been purchased, this would be a potential business between the vehicle owner and the service provider directly. Both the OEMs and the service providers would eventually pay service fees to run the service on the platform. These fees would go to, first of all, the home mobile network operators. And in the context of 5G-MOBIX, we of course always speak about roaming scenarios. So there would also be a business between the home mobile network operators and the visited mobile network operators as the roaming peer. 5G as a key enabling technology. Yeah, so there was a study by the consulting company McKinsey, which identified 4 major disruptions for the automotive industry. 5G is an enabling technology for all of these, at least to some extent, and it will play a major role in the development and the market launch of these. So the 4 pillars are autonomous driving, shared mobility, connectivity, and electrification. In 5G-MOBIX, and especially in the German trial site, we are focusing on 2 pillars. On the one hand, autonomous driving and connectivity. mainly even on connectivity. And in terms of connectivity, there are different paths that can be considered. On the one hand, there is V2V, so communication between vehicles. There is V2I, communication between vehicles and road infrastructure. But there is also links to roadside units, like for instance, some structure mounted on a rooftop. And in fact, these three different connections which I mentioned are the connections that we are considering in our use cases in the surround view sharing and in the platooning. And these are also standardized by the 5G V2X application layer standard. And so this kind of sets the basis for the further development of functionalities. So this concludes my introductory part. And with that, I'm handing back to Sebastian.
Yes, thank you very much, Christian, for your presentation. I will talk in the following and introduce you to our German trial site. What we have been doing in the German trial site, you can see some footage here. We are 4 partners in total: GT-ARC, TU Berlin, Valeo, and Bcomtech. The German trial site is located in Berlin, in the middle of the city, and we are doing our trials in open road in an urban environment. In total, we have 3 vehicles, SA level 4, which we have actually amended with 5G OBUs, communication facilities, and on top of the vehicles and OBUs, we have deployed vast roadside infrastructure across the trial site. Here, most notably, I would like to highlight the enhanced RSUs, as we call them, which are deployed at the roadside. You can see some small snippet on the top right, where the infrastructure perception gives the roadside digitalization of what happens in this urban environment. In addition to our eRSUs, we also deployed 2 roadside units on 2 different sites, which provide us with a PC5 side link for V2I communication. And we are using 2 different MEC infrastructures for our use case here on the German trial site, and that is the near edge MEC in Berlin from the company formerly known as Mobile Edge X, has been recently procured by Google, and we are using this infrastructure operated by Deutsche Telekom in Berlin. In addition, we also have a research deployment for MEC infrastructure here in our lab in TU Berlin. There are 2 use cases in the German trial site: eRSU assisted platooning and EDM enabled extended sensors with surround view generation. In the following, I'm going to introduce you to the overall concept of the eRSU assisted platooning concept. So on this slide, you see the complex infrastructure that we have realized in order to realize the eRSU assisted platooning. What you can see is basically the eRSU perception from the road being depicted by the different EDM circles or coverage areas. So this is where the different roadside units are perceiving information from the road and putting these perceptions into messages that are then transferred to the centralized MEC broker, for example, to collect the data from what we are denoting as service areas. And what you need when you have a cross-border, you need to realize 2 different areas. And what we have done in Berlin, we have basically split our deployment into 2 service areas and interconnected them by a geo-broker, which is then forwarding the relevant information. In this slide, you can see, for example, in the EDM5, there's an event happening in service area 2, and this gets forwarded via the geo-broker synchronization from the domain in the Deutsche Telekom non-standalone network, here hosted in the Mobile Edge X MAC, to the MAC broker being located in our TU Berlin research deployment. So the platooning assistance that we see here is basically consisting of two different aspects. One is the vehicle-to-vehicle communication to realize the platooning communication. And the second is this ERSU assistance flow, edge dynamic map flow that I just explained from the ERSUs earlier. In this slide, we have collected the different cross-border issues and the steps that are involved in trialing the platooning use case. Most notably, we have the communication being done either directly via PC5 messages, so that involves also the platooning messages and the roadside information, the edge dynamic map information coming from the roadside. And we also have the scenario where we have the communication being done fully over the 5G UU communication path. Or last but not least, the hybrid way of receiving information. That means that the EDM messages are coming in via the 5G UU interface directly to the OBU of the vehicle, of the platooning leader. And the platooning messages are transmitted vehicle to vehicle via the PC5 side link. This is also what we have depicted here in this step-by-step part of the platooning use case. I would like to note that we will see a video later on where this concept is explained in a bit more detail, so I will not go to the very details of this. The second use case at the German trial site is the extended sensors surround view use case. In this, we have a video stream that is generated by cameras, from 4 cameras creating a surround view. And this surround view is transmitted via 5G from the leading vehicle to the following vehicle. The architecture that we have deployed here is similarly as in the platooning use case, involving 2 different areas. So we have created a virtual border here for trialing the use case. And what you see here is the V2X application running on the vehicle with the vehicle discovery service client and the WebRTC component to transmit or receive the video stream from the leading vehicle to the following vehicle. We involve here the Edge Cloud from Mobile Edge X and the research MEC infrastructure here at TU Berlin, where the different MEC applications required to operate this use case are deployed. This involves the vehicle discovery service component, the MQTT broker, and the edge dynamic map data synchronization done by this MQTT broker. Similarly to the earlier slide on platooning, here you see the different steps that are involved in trialing the surround view use case. Also, it involves the cross-border issues that we have tackled for creating this or trialing this solution. Most importantly is that we have used an approach for dynamic QoS continuity and service continuity thanks to multi-modem, multi-SIM solutions. Details of this will follow in the next session, next slide set. Okay, having presented you the introduction on the German trial site, I will now move on to the 5G for CAM solution that we have developed in the project as an outcome of the custom solutions that we have developed. I will first start with the dual modem dual SIM solution, and after that, my colleague Angela Martin will give you an overview on the adaptive QS solution. Okay, so 5G-MOBIX being a cross-border project, we have created a custom solution to utilize multiple mobile networks. As you have, for example, in the context of cross-border corridors, where usually one mobile network operator coverage ends and the next operator starts. The overall concept is based on implementing a location-based switch of the mobile network from one operator to another. And in our concept, we are looking at switching the operator as an outcome of a decision-making component of a prediction function that exploits crowdsourced coverage maps. So this can be seen as an in-advance coverage hole notification that facilitates the proactive creation of a new session over another available mobile network with 5G coverage to minimize the mobility interruption time. In the figure to the right, you can see the 5G coverage on the German trial site by the O2 Telefonica network. And here you see that to the right, there's insufficient coverage for 5G. And this sort of coverage hole is what is crowdsourced in the approach that we present in the next slides. First of all, the scenario. So we have two commercial 5G NSA networks here for testing. So in addition to the O2 network, we are using the Deutsche Telekom NSA network, the commercial networks here. And we have created this virtual border directly at the location where this 5G coverage hole is located. So in this, we have two modems where each modem is associated with an MQTT application client to use the respective mobile network. And when the location X is reached, where the coverage is supposed to worsen or to stop completely, the connection is then established via the other modem's MQTT client, and thus switching the network when the coverage ends for the other operator. The hardware that we have used for this is the Quectel RM500Q boards with evaluation boards, and the Valeo Pica Volcano 2.0 TCU. In addition, we have used the Coda Wireless MK6C for the PC5 site link, and as an onboard PC, we have used ESS deployment. So for technical realization, we have created a V2X application that is interfacing with the GPS information from the Coda Wireless MK6C. And the received location-based trigger causes the change of the mobile network operator inside this Python script to call the Linux Network Manager command line client to deactivate the respective connection and activate the other connection. So there's two potential ways of exploiting a coverage map. You can either create a database for a full route ahead and store the switching locations locally, or you can subscribe for an in-advance coverage hole notification. On the right, you see the in-vehicle deployment of our dual modem dual SIM solution. In this slide, I'm showing you the coverage mapping approach, where a crowdsourced database is utilized, where the represented data can be visualized in ArcGIS. The coverage mapper architecture is depicted in the lower left. Here, the 5G modem is queried to collect the data relevant for the 5G network that is currently being connected. And this data is then stored in the MEC hosted database and can be queried to learn about upcoming coverage holes via REST API. And you can also visualize these as you can see from the measurement representation figure above. The in-vehicle deployment to the right shows you the approach that we have implemented. As noted earlier, we have the CODA MK6C, where the GPS signal is being utilized from. And we have the V2X platooning application, where the platooning application has the positions stored that are queried upfront, for example. As noted earlier, there's also the in advance coverage notification that can be used for this. In this picture, you see the predictive decision being implemented at a certain location. So here, in this example, you see at GPS position X, you will implement the network switch decision. And at position Y, you will implement the decision to switch to the other network, which has the O2 network SIM card. Let me come to the conclusions of this approach. True dual SIM, dual active functionality in 5G modems will, of course, at some point supersede the need to use more than one modem. So in 5G-MOBIX, we have been one of the pioneers in using 5G end-user devices. So initially, the use of a single modem did not involve the capability to have more than one connection at the same time being established to a network operator. Furthermore, with the eSIM functionality, the replacement of conventional SIMs will happen, and we will not need to place deliberately specific network operator SIM cards into the modems. So this more introduced flexibility will in the future lead to predictive QoS approaches, which will see a deeper integration in our understanding, and we'll see the V2X application side further evolving, including more intelligence and deeper integration with mobile networks. The German trial-side trials of our custom multi-SIM solution have shown the viability of utilizing the GPS position to implement mobile network switching decisions for the V2X platooning application. So in our platooning application, the ERSU assistance, as noted earlier from the roadside, is consisting of ITS messages, ITSG5 messages, and those are tolerating reconnections as long as you minimize the interruption time. In contrast to this EDM service, however, more complex stateful applications require the appropriate handling on the respective network application layers. So for other use cases, a more advanced handling and more controlled handling of this needs to be established on the different network layers. And with this, I'm done with my presentation part. Thank you very much.
Thank you, Sebastian. Angel, the floor is yours.
Okay, so I'm showing my screen. I hope that you already see my screen. Is that way?
Yes.
Okay. Okay, so thank you so much, Sebastian, for your nice introduction and the first half of the solutions that we have designed inside the Deutschland area site in order to try to mitigate some kind of situations and bad behavior around the performance that we suffer from the networks in order to bridge the the communications for 5G communications. So here in my slot, I will introduce another solution that is adaptive quality of service solution for this kind of applications. So I will just go over some different topics. First, I will start with the motivation in order to show you and to understand why we have done that work. Then we will move to the solution that we have implemented. We will have a brief look to some results, and then I will underline some conclusions that we have discovered somehow from our different experiments being done. Okay, in terms of the motivation, so as already Sebastian has presented, and in order to have a more simple view, even if the diagram is not much simpler, but at the end, what we are trying to do is having two different vehicles send the information in this specific solution related to video streaming to the other vehicle that is on the rear position. This way, this vehicle A could understand what is upcoming in the road coming from vehicle B. And for sure, in order to allow this communication, as they don't know each other, and they could be even using different carriers, different mobile network operator subscriptions, they will need something, a common infrastructure in order to trust and to find each other. For that, we have used the MEC solutions that, for example, Sebastian has introduced related to mobile checks or to the day labor cloudlet. And once the general umbrella of the situation that we want to perform has been presented, let's have a look to the different issues that we have there. So I will go very briefly to some different topics, but we could imagine that there are some topics related to regulatory aspects and other ones that are related to the technical ones. From the regulatory point of view, we will need, as I have introduced previously, a MEC in order to perform the handshake, the negotiation, to meet each other, the different parties, because here in this scenario we don't have vehicles that are accessing to or consuming services from the internet or from the MEC. They are establishing a session with other vehicles that are in the surrounding area. So, and for that, MEC is an ideal approach. Then we have privacy, because the data that they are exchanging are needed to be encrypted in order to secure the communications, and is something that also is needed to be there. Then we have, from the technical point of view, that the radio access network from the cellular networks are not tuned, are not ready, or are not specifically targeting this kind of applications. They are mostly designed for content consumption. This means that download is much bigger than upload, and that the quality of service is highly heterogeneous, depending on time, depending on concurrency, depending on the geoposition of the different participants. So you have to deal with very highly changeable conditions in terms of network performance. Then we have another problems that are there. We have NATs, because it is a peer communication, and ideally the mobile networks are not designed for this kind of communications to establish the communication that we are doing right now, a video conference somehow. They are not favoring this kind of applications, because they have NATs that the communications has to cross different domains, because they could have, as I have mentioned, one vehicle could be subscribed to Deutsche Telekom, another one could use Vodafone, and there are different networks that we need to bridge from end to end. And the thing also, the problem also here is that the canonical MEC is not accessible for different subscribers. So if I am accessing, or if I am establishing a session through the MEC of Deutsche Telekom, I cannot access from a Vodafone user. So this is also something to take into account. And for sure, for that kind of communications, we need a quick bootstrapping. So we need to establish all the handshake and all the negotiation very quick. And what can the standards to do in order to support us or to help us in order to accomplish that kind of applications. So we have WebRTC, that is a standard in order to perform video streaming communications between peers. Here we have solutions that are already there, that are default in order to perform security, to have encryption, to perform the handshake in terms of exchanging the different credentials, to be net transversal and be able to go through different network infrastructures that are there, to secure everything, and also to be able to favor that one vehicle could send their communications, their video sensors to a set of vehicles. And then we have also a H.264, that is the video standard that we have used in our test, that where we have another ones like high efficiency video coding, versatile video coding, and so on. But the thing is that we can find a universal hardware acceleration in a lot of solutions and hardware and equipment that are already designed for vehicular apparel. Okay, what is our implementation for the adaptation of the quality of service? We have defined 3 different levels, and based on different metrics that we capture from monitor metrics that are already there in the WebRTC, we have the bandwidth, the round trip time, and the jitter, and depending on that values, we have identified different thresholds, and we move from one to the other. What we do, we upgrade or downgrade the bit rate, the sample rate, so the number of frames per second, and the resolution. And all the time, what we have in mind is that this kind of video streams has targeted to be consumed by a computer vision system, so the different levels and so on are designed in order to favor that these kind of applications are still valid and can process that kind of video streams. Okay, so another thing that is also in the design of this application is the where to start in these 3 different levels. We always start from the poor level. Why? Because this way we is that the startup time is fast, and we don't have a high demanding need of traffic at the very beginning when we are bootstrapping the session between the different vehicles. Okay, so in terms of the testing scenarios, we have tested 2 different scenarios. The ones on the top that where we have problems in the connection in the uplink or other downlink. In this case, we have the MEC that not only is being used in order to perform the signaling and the handshake, it is also a gateway that all the traffic goes through it. Why? Because sometimes, depending on the configuration of the network, on the networks that are being used, the direct communication, that is the one that is on the bottom, where the handshake is performed through the MEC, but then the vehicles can communicate each other directly. Directly, I don't mean PC5. Directly, I mean without gatewaying anything through something that is on the internet or something that is on the MEC. Sometimes this bottom scenario is not possible, and we need to have this MEC that is providing to the one that is encoding and applying the different configuration in the video streaming. I mean the resolution, the frame rate, and the bit rate to adapt to what's going on in the network. Okay, so what are the results that we have identified? The first thing is that as the prompter you do, or the frequent you do the monitoring of the metrics, the quicker you are able to react. Okay. The 3 different levels also is good in order to favor quick reaction, but at the same time to avoid ping-pong effects. So to avoid, we could have 10 different levels, but the thing is that then what we notice is that we change a lot between different levels. So it's better for the computer vision applications to don't switch so frequently the conditions in order to have a kind of a steady performance. And then in terms of the gateways, what we have identified is that it includes, or it aggregates some latency for sure when compared to the direct communication. That is the ideal situation, but is rarely possible in at least in commercial networks. Okay, and what are the results that we have? So based on the open source implementation that we have done, it takes 2 seconds or more or less 2 seconds in order to get notice of something is going wrong in the network coming from the RTCP metrics. We really think that is something that can be improved, because it's mostly coming from the implementation that we are using based on open source solutions. And the other thing is that the time elapsed from the moment the video in the sender is changed to the moment the receiver noticed this change is more or less like 700 milliseconds. This is mainly based on the buffering that we included in the gateway and in the receiver in order to avoid visual artifacts that comes from high jitters and bad performance that we often see in the networks. Okay, so my last slide about the conclusions. Obviously, coming from our tests, the cellular networks are not tuned for vehicular communications. They are prioritizing the downlink over the uplink. So we can see here very different pings, very different download and upload, where always the download is much higher than the upload. And even sometimes the performance is very, very poor based on the time day, based on the concurrency of users, based on the geoposition. So the SICAM applications need to struggle and to meet this kind of situations. The third one is that the visibility of what's happening in the network is myopic in terms of, as far as we have a gateway, the gateway knows what is happening in both sides, in the uplink and the downlink, but the origin only knows what's happening from the connection between him and the gateway. So in order to have a head-end view, we need that the intermediaries also are able to transfer this information, these metrics, to the different peers. Another situation that we have also learned is that the canonical MEX has very huge and very difficult limitations to address by these kind of applications where we have peers. So you have something that comes from the vehicle to a service that is on the MEC or internet, this kind of problems, you don't have it. But as far as you have different vehicles that could be in different mobile network operators or in the same one, this kind of the MEC could be a problem, at least the canonical one. A cloudlet sometimes is a solution. And as a main highlight of my in my presentation is that quality of service techniques are essential in order to be able to enforce the SICAM applications to deal with what's happening in the networks. So that's all I have to tell to you. Then I will pass the floor to Fikret, who will introduce from GTARC the trial results more in detail. Thank you.
Thank you very much, Angel. Good morning, everyone. Yeah, we will now focus on selected results that we, as a result of the measurement trials that we have carried out at our trial site, as presented for the 2 use cases, platooning and extended sensors scenarios. And in doing that, we will actually start with a brief set of agnostic, so-called agnostic tests, so scenario agnostic tests. This is mainly to kind of set the baseline to get an understanding of the environment we have in our trial site and the channel conditions, etc., which helps us also better interpret the results in the scenario testing. Yeah, then we will have the main section focused on these platooning, which with the RSU, with the edge support, where we will be focusing on two network flows. One, the platooning control messages that are exchanged among the vehicles, and the so-called edge dynamic map messages, as Sebastian introduced. In our scenario, we have the roadside units also providing kind of an infrastructure perspective to the vehicles, so that we can detect, for instance, road blockage, etc., that are then disseminated to the related vehicles, enabled by the MEC application running on the RSUs and on the remote or network host cloud environment. For the extended sensors with surrounding generation scenario, we again look at two different network flows. One is the video stream, so that's the focus for this higher bandwidth demanding traffic scenario. A real-time video streaming case, we will look at vehicle to vehicle, again not directly via PC5, but network routed vehicle to vehicle video streaming case. And to establish the peering and connectivity among the vehicles, also MQTT messages are used. So this is traffic between the vehicle and the MEC instance. And in general, based on the scenario and according to the relevancy of the related metrics, we will look at the selected KPIs of throughput, latency, and reliability, or packet loss, represented in either form. Yeah, as said, we start with the agnostic tests to understand the baseline in our environment. And from the beginning, as a disclaimer, we are utilizing commercial 5G NSA networks, in our case, in Berlin city center. So these are Deutsche Telekom and O2 networks. And what we present are obviously some aggregated results over the measurements done throughout several days and weeks. And this is the results are specific to our trial site and to the specific cells we have at those certain locations. So these, of course, should not be generalized as a performance comparison over these networks and MNOs. Yeah, but just to quickly have an understanding here, we see, as expected, a huge, quite a big difference between downlink and uplink performance. Let me try to highlight here. So what we see here are, as said, aggregated results. To keep it simple, just represented as average and peak values, for downlink, Deutsche Telekom, then for downlink again for O2. And the values in general are quite okay for our use cases, for our purposes in the tests that we have carried out for the Berlin or German trial site measurements. But we do have corner cases, especially when we look at, so this was the good coverage, so somewhere in the middle of a cell when we are stationary, and when we have good coverage, these are the results reflecting that. But we also tried through careful analysis of where the edge cell edges are located, and conducting measurements at those locations against stationary. But when we don't have a good quality signal, and there's of course a significant reduction, especially when we look at the uplink. In some cases, this may then turn into a bottleneck. This we will get to it also at the end, but here from these results we already see the traditional 5G deployment or cellular mobile network deployment patterns of the imbalance between downlink and uplink, which is not fitting well, as known, to some of the CCAM connected and automated driving use cases applications, because the vehicle is often also a source of traffic, and uplink bandwidth is also important, for instance, in our extended sensor scenario with video streaming. Then we also show here the mobile scenario where we are moving along and within the cell from good coverage to cell edge. As said, these are aggregated results, the details of which are reported in the upcoming deliverable 3.7. So we are submitting this already at the end of this month. So hopefully it will be public in the upcoming months. So for details, one can refer to this. And finally, we also looked at the UE or vehicle entity to the application server latency. The average values that we see here, especially for Deutsche Telekom case, are quite good and acceptable, again, for the CCAM use cases in question. And the big difference that we see here for the O2 case is mainly due to the configuration we have at our site. With Deutsche Telekom network, the MEC entity that we are using is from Mobile EdgeX, which is integrated and hosted at the Deutsche Telekom data center. It's actually at a gateway in Berlin, so that's definitely an advantage to keep the links and the latency smaller. In the O2 case, this is we don't have an integrated MEC in the data center there, but we are connecting through the O2 network to our experimental edge node hosted at TUB campus. So there is no direct peering, and we are connected via the open internet. So that explains the larger UE server latency. But this is sets as at least as a baseline understanding of our environment to guide the tests and insights from the scenario testing. Some more insights on these agnostic tests, and this time we are looking especially into the MEC and inter-MEC connectivity, because as we have already seen in the scenario descriptions and in the description of the German trial site, we rely heavily on edge servers and their interconnectivity. So when we consider this cross-border operation, and we have two MNOs on the sides of this border, in our case the emulated border, we have different MEC entities operated and hosted by different MNOs or different stakeholders. And in the scenario, we do have the interconnection and knowledge sharing, information sharing among these MEC instances. Therefore, we also wanted to study, again, independent of the user story or use case, the agnostic test of the round trip time among these MECs. We actually considered three MEC locations or three MEC server instances. One is the TUB, as said, the experimental TUB MEC that we are hosting at the TUB campus, connected to the TUB campus network. We have the mobile EdgeX server located at the Berlin gateway at the Deutsche Telekom data center. And we also use Amazon Web Services as a benchmark here. So that's like a public cloud instance, not telecom hosted, but a public cloud instance, a commercial cloud instance. We have not deployed and used this in our actual scenario testing. This is as a benchmark to see the difference between the cloud-led telecom hosted mobile EdgeX, for instance, versus the commercial cloud on something like Amazon Web Services. So what we see here is actually close values for the Amazon Web Services and mobile EdgeX from the TUB hosted MEC. There can definitely be some improvements in the configuration of the mobile EdgeX case, but we see that this is not too different currently in our tests from the commercial network of Amazon Web Services. And in the case of MEX MobileGX versus Amazon Web Services, this is even slightly less. This could be partly due to TUB network being shared, the connectivity being shared via large campus network, and the connectivity between MobileGX and Amazon Web Services may have a better connection quality in general. But we see that there is roughly about 20 milliseconds of extra delay caused by these inter-MEC connections, which is part of our scenarios in many cases. And there's not a significant difference between the different pairs of MECs that we have studied. Finally, the last agnostic tests that we provide here is the RTT from the roadside unit at the local trial site we have here in Berlin to the MEC instances, to these 3 MEC instances. So the roadside unit is located at our campus network and connected directly also to TUB, to the same Ethernet network. Therefore, on the right-hand side, the gray colored results definitely have the least delay, RTT time, while that of Amazon Web Services and MobileGX connected via 5G from the RSU are a bit larger, in the order of 40-45 milliseconds, which are still acceptable values, good values, but there is some definitely variation in the different data instances. And in this case, we see that the 5G RSU connectivity through the telecom network, Deutsche Telekom network, to the MobileGX instance within the telecom network does provide an advantage because of the proximity of the entities within a single operational domain. So now we will switch to the scenario testing, but before that we would like to show you a compact version of the demo video that we had prepared earlier. A more detailed and longer version of this is also available publicly, either directly on YouTube or through 5G-MOBIX website. You can access that version as well. And I would ask Sevi or Julie to please start the video for this.
Yes. 1 second.
Thank you.
All right, 1 moment.
Okay, thank you, Sylvie, for that. So I think we are back with my presentation. Hopefully you can see it. Now we start with the scenario testing results, and we start with the ERSU platooning case. I've already mentioned the network flows, and now we will look at 3 different configurations. The first configuration is where we have the PC5 side link communication used for both of the flows on the left. In the UU case, on the opposite, we use the network router traffic, the UU interface for both of the flows. And the hybrid case is where we have the vehicle to RSU communication via UU and the vehicle to vehicle platooning messages via PC5. So starting with the full PC5 case, we see that the end-to-end latency and packet loss actually are highly fluctuating depending on the distance and line of sight. The values are quite acceptable, quite good for the scenario. But I first need to give you some background on the plots. What we see here is actually statistics over 10 separate runs. So the x-axis is showing these 10 separate runs done over time, and the tabular values are the statistics over the whole set of these runs. So in the interest of time, I wouldn't be able to go to or I shouldn't go into the individual data values or details, but try to highlight some key messages, and we will move quickly to the key messages at the end, or observations and conclusions, so that we have time for the last session. So this was a full PC5 case shown for the EDM flow. So this is the roadside unit to vehicle, the messages exchange of PC5. And this is the platooning flow, again, running through the PC5 side link interface. Similarly, we have quite good and even better latency values, because the vehicles have closer proximity and the channel conditions are much better. So we have definitely a better latency and packet loss or reliability performance through the PC5 full PC5 interface. But I said the downside is that there is high fluctuations. We have observed that when there's a large truck, for instance, parked on the side, and which intermittently blocks the line of sight from the vehicle to the roadside unit, then there is strong reduction in the performance. The second configuration was the full UU case. This is where both the EDM flow and the platooning flow are running through UU interface. Here we see significantly higher latency values, as you see. And in this case, we also, since we have 2 MECs involved in the pipeline, and around the border, we do have the involvement and interaction of the 2 MEC units. We looked at one case where we have only the mobile ejects in between the RSU UE communication, so this is the EDM flow. And in another case, we have both TUB MEC and mobile ejects MEC, 2 MEC instances in the pipeline. So this is aligned with what we have seen in the beginning in the agnostic tests for inter-MEC communication overhead. But as we see for the UU test case, of course, this is now fully reliable connectivity, which is running over TCP. But the mean values are quite high, and there is really high variance also for this case. Then for the platooning case, again running over UU in this full UU scenario, the latency is again definitely higher compared to PC5 as expected, but as said, we have fully reliable links. So in this case, reliability KPI is not relevant. Therefore, here we just selected another KPI, the data rate, basically. But of course, for this platooning messages, we don't need so much throughput or bandwidth. Therefore, here we see small values. More important and interesting is the hybrid case, where we have then tested how it the application behaves when we run the EDM flow through the network. So this is the vehicle to RSU communication running through the UU interface, while the platooning flow is running through the PC5 side link interface. And here we see that the latency for EDM flow is actually improved because we are not running two separate flows over the same UU interface. We have less competition, less interface for the channel. So this is an improvement. And again, we have full reliability as an additional benefit on top of the PC5 case. And on the other hand, for the platooning flow, in the hybrid case, again, we are using the PC5 side link. The latency is quite good, as well as the packet loss or the reliability is also good. So the hybrid case, we can say, is kind of providing best of both worlds in our scenario, and it makes sense to use this mode, at least in the current 5G network configurations. We do expect improvements in the upcoming releases with the new features, additional features of network slicing, especially URLLC of 5G SA networks to improve this. But for the moment, PC5 should be the choice for the time-critical messages, especially directly between the vehicles, and the UU interface for the reliable messages. And overall, we have observed that we have very dynamic and variable channel conditions in this urban environment we have. And as a final remark, we believe that a smart selection of the different mode, PC5 versus UU, makes sense, not to do this statically allocated, but to, based on the channel conditions, on the environment, to make this in a more dynamic way, which should rely on a predictive QoS module. Quickly moving on to the extended scenario user story trials. I talked about the network flows, and here we are now focusing on measuring with the difference between constant bitrate CBR versus the adaptive bitrate video streaming case, and we will look at data rate and reliability as the KPIs. And for the MEC-enabled vehicle discovery service, this MQTT messages, we will look at the latency as a KPI. Just to set the stage, this is showing the CBR versus ABR video streaming. The data rates for the CBR set to 10 megabits per second. The results show that there is some packet loss, providing a data rate of 8.8 over this 10 megabits per second CBR video. And in the adaptive bitrate case, we observe that there is significantly more efficient utilization of the channel with the adaptive bitrate without much perceivable quality degradation in our scenarios. Perhaps a bit more interesting is the reliability case, where we also observe that adaptive bitrate case also improves the reliability, reduces packet loss. And then finally, for the MQTT messaging results, we analyzed uplink and downlink connectivity separately. And the results here are at least looking at the mean values on average in general are quite good and acceptable, but we do have, again, fluctuations due to the channel conditions, and some outlier data can go even up to a full second, while the mean is around 35 milliseconds, for instance. And we also see this imbalance between uplink and downlink, where we have much better conditions. When we look at the max values, especially, we have 1 to 3 ratio compared between uplink and downlink. And finally, one key message out of these results, it was mentioned briefly by Angel as well. We have been using these commercial 5G NSA networks, and through this practice of using such commercial networks, we have noticed some practical implications of such networks. In many CCAM scenarios, we do need the direct peer-to-peer UE to UE connectivity, but this is generally not a feature supported directly by the MNOs. So therefore, there are different solutions around this, either using specific APN configurations to support such so-called public APN accessible public IP accessible IP to UEs, or we need to use not traversal mechanisms through MEC. But then, as you see, the interruption time, the reconnection time when we switch from one to the other is much more significant with this not traversal MEC case in the order of 10 seconds. While if we have support for public IPs, publicly accessible IPs for end-to-end direct UE connectivity, then this becomes significantly less. With this slide, I will conclude some of the key messages that we have already covered. Adaptive bitrate is increasing definitely reliability. We talked about this public IP issue just now. We have seen also earlier that the latency of the UE to MEC connectivity is about 30 seconds, 20 milliseconds, 30 milliseconds, which should be expected to be much better than connecting to a public cloud instance. But currently, this is not the case in our setup, even though we have MEC mobile AJAX server deployed on a Berlin gateway in the telecom data center. There is definitely room for improvement in this case. And in general, we definitely have very high variability in network performance when testing on the open nodes on these NSA networks. So with that, I apologize from Gorka for taking some of his time already, and I will quickly hand it over to him now. Thank you.
Thank you, Fikret. Let me know if you cannot see my screen. Well, as Fikret said, I think we are a bit late in the agenda. Sorry for this. I'll try to speed up in my session. But it's about the lessons learned we have obtained in the project in the context of the German trial site. We have classified the lesson learned in 3 different categories: technological, regulatory, and reliability and availability. This is how we have presented these lessons learned in a common template using this table. So first, we have the requirement that needs to be satisfied from the point of view of the CCAM application. And then we explain if this requirement is satisfied with the current or the state-of-the-art technology, which is the impact of not satisfying this requirement. And finally, the workaround that we have followed in the German trial site to minimize or mitigate the impact. Okay, so the most obvious one in the context of 5G-MOBIX is the requirement of seamless roaming. As you know, this is not satisfied because current networks do not support cross-border CAM services due to long disconnection times. The workaround that we have followed, that was already explained by Sebastian at the beginning, is the use of dual modem and make service to use equipment to assist the roaming based off positioning of the beacon. Regarding the dual modem, the requirement for the CCAM will be to have again a seamless dual modem inter-P element switch. So this meaning that the backup network interface is immediately running before when one user equipment is disabled, but this is not unfortunately satisfied. And the transition between the UEs is not instant, and application system is temporarily disconnected. The workaround, also explained by Sebastian in detail, using the router to the forward traffic through one of the other user equipments where both are enabled. Regarding the MEC discovery, the user equipment do not know the address of the MEC endpoints, so a MEC discovery service is required to be implemented in the application layer. In our case, we have implemented a MEC registry in a cloud, compiling available MECs, and a MEC orchestrator deployed in each MEC to manage the MEC handover and data sync. Regarding what we call here intra-MNO or inter-MNO UA IP visibility, meaning that the user equipments in the same area for the same or different MNO can communicate each other through UDP sockets. This has been explained also by Angel in his session. This depends of the network configuration, but sometimes it's not satisfied. So the workaround here, we have two options, using an APN that provides a public IP to the user equipment, or a gateway installed on a server and publicly available in internet. Regarding session continuity, meaning maintaining ongoing IP sessions while changing from home PLMN to the visiting PLMN. So this means that the SSC mode 3 is fully established. This is not the current status. The impact of this is that the TCP UDP sessions are required to be renegotiated, and the KPI measuring tools need to support IP changes. This is also an issue that we found during the trials evaluation stage. There is no workaround from our side, from the side of the CCCAM developers, and vendors need to work on SSC mode 3 implementation. Regarding 5G standalone compatible user equipments, this is not always satisfied. I mean, the 5G standalone specifications are on the roadmap of vendors, but this support is not always solid or even implemented. At least is what we have experienced in the framework of the project. This has meant a lot of time in testing several options, trial and error, while 5G technology implementation consolidates. So we have tested different vendors, firmware versions, and also smartphones. But we think that this will improve while the 5G implementation increases or gets more mature. Okay, in terms of regulatory lessons learned, temporal permissions for experimental networks. This is not something, let's say, straightforward. There are tight regulations, complicated and long procedures with public institutions requiring detailed or prototype equipment working in a specific band that is agreed after an initial study, and the permissions ends after some months, and it is dependent on a range of unexpected commercial actions. This means the impact is that it is difficult to invest in an experimental setup with a lot of conditions to ensure availability. So from the point of view of regulation and public authorities, they are not giving us a lot of help or assisting us a lot. So the workaround that we have followed in the German trial site is the use of commercial networks for the outdoor tests, as was already explained by Sebastian at the beginning. Regarding reliability and availability, there are in our user stories several requirements in terms of downlink, uplink, packet loss. These are not always satisfied, even if they are not very demanding. It depends of several factors that are out of the control of the CCCAM developer, and that have several impacts, like visual artifacts on server disconnection, in the video streaming, connection failures, and so on. For the video streaming, as Angel already explained, we have this workaround of quality of service bitrate adaptation that mitigates this problem, especially the packet loss problem, but also makes the solution run with lower bitrate. Regarding the MEC latency, this is not always satisfied. Sometimes there are big latencies. We have experienced this also even with MECs, and the jitter buffer can help mitigate the effects of this. Regarding steady handover and roaming control in commercial networks, meaning that the networks that not tries to avoid ping pong between cells and PLMNs. This is not always satisfied, unfortunately. The impact is Hanover, that is performance degradation, or roaming, service interruption, constantly, going from one to the other. The workarounds here is a dual modem for roaming, but in the Hanover control is not in the hands of the CCCAM developers. So the 5G vendors and MNOs need to have this under control. So, well, the conclusions for these lessons learned is that not all the requirements of the CCAM use cases are fulfilled with current technology or network deployments, at least in non-standalone, which are not in the hands of CCAM developers. So CCAM developers need to implement some workaround to avoid or mitigate the negative impacts of these unsatisfied requirements. So this is all from my side. Thank you, everybody. Sorry again for the delays in the agenda, and I will let Sevi continue with the question and answer session. Thank you.
Thank you. Keeping an eye on the time, yes, we are over time. But since there are only a few minutes left, perhaps we can take some questions. All right, I can see one coming in from Fotios Amelis. The ULDL requirements on slide 6, were they per vehicle? If so, can the network capacity become a bottleneck in case of many vehicles? I guess this for the last presentation.
Okay, so can you read again? I mean, it was slide 6 about downlink and uplink. And the question, because I don't see it in the chat, so can you repeat it again? Okay, I think it's there, right? Mm-hmm. One moment.
Okay, it's about yeah. If it was per one vehicle, if the network capacity becomes a bottleneck,
Yeah, that's also true. One of the differences, I think, or the advantages of testing in open roads is precisely that you can test in real conditions with the network capacity, the number of user equipment that are connected. That is also a big factor to take into account. So sometimes also in this kind of projects, they force us to use autonomous driving with closed roads, where nowadays is there at night, but this is not real conditions. And in the real conditions, there are a lot of users in the area, maybe pedestrians or people inside a bus also consuming streaming videos, and this also counts in terms of the capacity. So yes, it is a very interesting point that need to be further studied. Thank you.
Thank you, Gorka. Another question for you. In order to guarantee an acceptable service, do the MNOs allocate a slice or CAM?
Yeah, the point is that the slicing is not yet deployed, at least in the countries that we have been trialing, that in Germany, Spain, and Portugal is called for the corridor. But yes, slicing will help to achieve these KPIs of CCAM. I think it's one of the main features of the 5G roadmap.
And perhaps for Sebastian, as we allow some time also for more questions to come in. Could you perhaps tell us if you expect the 5G performance to improve in the future for the platooning control messages via 5G UU?
Thank you very much for that question, Sevi. Yeah, definitely what we have seen in the results of the German trial site the platooning control messages exchanged via 5G UU interface are not fulfilling the expectations and would not motivate using this for commercial application, so to say. So what we expect in the future to happen, Fikret has already indicated this in his presentation, is that with network slicing and especially with the URLLC configuration, the slicing would ensure that the low latency requirements for this particular flow could be achieved. One major aspect that would hopefully help in this is the deployment and activation of 5G standalone mode, because the current 5G non-standalone networks that we are also using in the German trials, they do not yet benefit from the latency improvements that are standardized in the release 15 and onwards of 3GPP. So basically, the realization of the 5G standalone and in connection with network slicing are expected to help using platooning flow over the 5G network.
Thank you for this answer, Sebastian. Well, there was more time for more questions, but I'm afraid we have come to the end of our planned agenda for today. Is there anything else you want to touch on before we conclude the webinar? Any of the panelists?
Well, I would like to thank everybody for joining in, and if there's any question beyond, please feel free to get in touch. And yeah, thank you very much.
All right, thank you as well. Thank you to all the speakers for your insightful presentation answers. And thank you all for joining the webinar. Really appreciate it. Before we sign off, and I hope we move to the next, here we are. I would like to remind you that there are some upcoming webinars this week. Tomorrow, actually, at 3, we have a webinar on the results and lessons learned from the Dutch trial side. And next week on Thursday, we have another webinar from the South Korean, from the 5G-MOBIX South Korean trial side. So we hope to see you there as well. If you would like to rewatch this webinar or any of the previous and the upcoming webinars, make sure to check the 5G-MOBIX website. They would be uploaded as we go. And again, many thanks to everyone. We hope to see you soon, and wishing you all a lovely day ahead. Thank you, everyone.
Thank you, Jerry. Bye.
Thank you. Bye-bye.
Thank you, everybody. Bye-bye.
Thank you. Bye-bye.